Now that we've developed a fairly full understanding of the current and the behavior of this RC circuit, this resistor capacitor circuit, it's time to get back to our final initial question, which was, as this capacitor discharges, how much power, how much energy actually ends up dissipated through the resistor? How much energy are we getting out? And ultimately, will that energy match the energy we hope we've been able to store inside the capacitor system? So this brings us then to our final computation in this unit on the capacitor, which is the discharge energy. Now, to compute this discharge energy, recall what our plan was at the very beginning. We had decided that the energy that comes out of this system is going to equal the integral of the power that is coming out of the system, integrated with respect to time, during this entire discharge process. Now, the discharge process starts at time t equals 0, but it's important to keep in mind that this discharge process continues on towards infinity. It's exponentially decaying, so past a certain amount of time, it's practically completely finished. But if we want to get every last drop of energy accounted for, we actually are going to have to integrate over all possible times, up to infinite time. Now, where is the energy coming out? How do we access the energy? Well, as the capacitor is discharging with its current I, that current I is flowing through this resistor. And that's where we're getting energy out of the circuit. That resistor will heat up or produce some light or some other process. So it's the energy that's dissipated in the resistor, the power dissipated, that we're actually trying to account. And we have had in the past discussions on that power output, and we know that the power that comes out of an electrical circuit through a resistor is equal to power is energy per time, and that's equal to, if you recall, that's energy per charge, voltage, times charge per time, current, would give us energy per time, or power. And in the case of a resistor, we know that V actually equals I times R. So substituting this all in, we find the power that comes out of the resistor is I squared times R. And so that is what we need to integrate. So we're going to be integrating from 0 to infinity, the current squared times the resistance, where the current is equal to, where is our value here for the current? We had a formula way up here, right? It's Q naught on RC times our exponential. So this is going to be Q naught divided by RC times our exponential, e to the minus t divided by RC. That is my current, which has to be squared. And then that has to multiply the resistance, where this is I. So I'm actually integrating I squared times R. There's my resistance. And then that is integrated times time dt. All right, so we have this integral to do. And what are we hoping for? We're hoping that at the end of the day, it's the initial stored energy in the capacitor. That's going to be the big question. Is this really going to be our initial energy, 1/2 Q naught squared over C? That's the big question we're asking ourselves. Well, it's going to be a math problem from now forward, but let's see how well we do here. Okay, let's hope this works out. Okay, squared, so I'm going to have to square this quantity. I'm going to get, and these are just constants, which I can pull out of my integral. So in the squaring process of the constants, I'm going to get Q naught squared will come out, Q naught squared. It's then divided by R squared, which multiplies R. So that's going to be divided by 1 power of R. I have C squared in the denominator, so I'll write C squared. So I've taken care of R, Q, and C, and I've gotten the powers correctly. So what's left then is this integral from 0 to infinity of e to the power Now I'm squaring my exponential. Remember, squaring an exponent just doubles the exponent. So this is minus 2t divided by RC, and that's integrated over time dt. We're getting closer now. I can reproduce my constants. Q squared on RC squared. Oh boy, it's almost going to be a miracle if this thing works. Now, I need to do my indefinite integral, and I think you guys know how to do this. It's an exponential function, so we're going to guess it's going to be, the integral has to be an exponential function, 2t divided by RC. And our job then is to make sure that we put in whatever factors here are necessary so that when we take the derivative of this combination, we get back our original function. Well, if I take the derivative of this, I do get back my original function, but I get some factors I don't want. I'll get minus 2 divided by RC. So I have to multiply by the inverse of that. I'm going to have to multiply by minus RC here divided by 2. So that when I take the derivative and I get a factor of minus 2, that'll kill my minus sign in my 2. I'll get a factor of 1 over RC. That will kill my RC up here. Good. So I've got the indefinite integral, and I should remember to evaluate it between my limits. Coming now down to the home stretch. We're starting to see some promising looking combinations. I've got the half here. This is starting to look pretty good. Okay, so this will equal Q naught squared on RC squared. Suspense is getting to me here, folks. All right, now we stick in the limit at infinity. So when we stick in that thing at infinity, we'll get minus RC divided by 2 times e to the minus infinity. But of course, e to the minus infinity is 0. So that term doesn't do anything for us. Then I get minus the next term when I stick in the 0. So remember, you put in the first term. I'll put that in square brackets. Then you subtract off the same quantity, RC over 2. But now you do it where you insert the lower limit, which is going to be 0. So I'll get e to the power minus 0. And of course, now e to the minus 0, that is just 1. And very nicely here, I've got these two minus signs, so those will cancel. So I've just got this term here to combine with this term. So let's see. Oh yeah, this is going to work here, right? Because the resistances come to papa, right? The resistances cancel. The capacitance in the numerator will cancel one capacitor in the denominator. And I've got a factor of 2, so there's 1/2. I've got my Q naught squared on top. Oh yes. And all that's left, I've accounted for everything over here, is just, I've taken care of the 2, the Q squared. I just have one factor of C on the bottom. And yes, absolutely, that we got out of our circuit every last drop of energy we had put in the beginning. This matches. And once again, we have a very happy professor because energy is truly conserved. More happy professor symbols. And I thank you very much for lasting through that. But as you can see, energy conservation really does work. We really can use the capacitor for an energy storage device.